So yeah, this is one of the projects I've been working on lately. It's a large-scale Unity battle scene with 1,000 Mike Tysons going up against 200 gorillas. It's got that UEBS2-Style chaos on screen, but on the hood there's actually a lot of systems working on. So in this video I want to break down how some of this stuff works. So yeah, before jumping into the actual setup, here's the rough breakdown of the video. First I'll go through the LOD part, then the GPU instancing and crowd animation side, and finally the formation system. Let's start with the LOD. The basic idea is pretty simple. Characters near the camera keep more detail, and characters farther away use cheaper versions. In Unity, I'm using a plugin called Polyfill just to speed things up a bit. It gives me a quick way to generate simpler versions of the mesh for different LOD levels. I'm keeping a few preserve options on so the UVs and mesh boundaries hold up better. And I also use the tolerance sphere to protect areas that I don't want to reduce too aggressively. Alright, now we're moving on to the GPU instancing and crowd animation part. So this is the basic idea of GPU instancing. Instead of the CPU handling every single character one by one, it first prepares a list of instant data. That list just contains the key info for each copy, like position, rotation, scale, or variant. Then the GPU can use that list to render a lot of similar objects much more efficiently. So I'm not really using the animator in the traditional way. It's basically just acting as a container for the animation clips, and then the crowd manager using that to bake the animation data. Now over here in the crowd manager, I registered the prototype Mike Tyson, hook it up to the animation source, and bake the animations from there. Once the bake is done, it generates the baked animation data, including an animation texture that the crowd system can use much more efficiently. This is the animation texture. It looks kinda crazy at first, like random colorful noise, but it's actually storing animation data, and this is a cleaner way to think about it. Along the x-axis, the data is split into different clip ranges, like clip 1, clip 2, and clip 3. Then inside each clip range, the frames move forward over time. Along the y-axis, you've got the bone index, so each row maps to a different bone, so basically this texture stores the pose of each bone across the frames of multiple animation clips. Once the animation data is baked, the next question is how does each Mike Tyson actually use it, and the idea is pretty simple. Each instance just carries a few values with it. So for example, clip index tells it which animation to play, time tells it where it currently is in that animation, speed controls how fast it plays, which can be used if I want to blend between clips, and then the transform data handles where that Mike Tyson is in the world, plus its rotation and scale. I'm using what I call the personal bubble system. It's basically just a role-based spacing rule around the enemy. The important part is that the bubble isn't identical for everybody. It gets bigger as the row moves farther back, so the front row stays nice and tight, while the deeper rows naturally keep more distance and create more depth. I'm not increasing it in a fully linear way either. It grows in stage, which helps the front stay compact while the rear opens up more. The bubble gradient is a big reason the formation holds together. The next big problem is target matching at the front line. Once everybody gets into the fighting range, I need a reasonable way to figure out who should fight against who. If I just use nearest target logic, things get messy really fast. Units start cutting across each other, the middle gets too crowded, and the whole line kinda folds into a funnel. So right now I'm handling it in 2 steps. The first step is projection. I build a sideways axis from the squad's movement direction, and then I project both my unit and the enemy onto that axis. That gives me a simple lateral value for each one, basically a left to right position inside the line. Then the second step is scoring. I use that lateral information to score possible targets. If an enemy is closer to my lateral position, that usually means it's a better match. I still include a small forward factor, but the lateral match is usually the main idea here. And yeah, my current algorithm may not be perfect, so if you've got bad ideas for the algorithm, feel free to leave them in the comments below. I'm gonna keep working on this project, and in the next video I may release some early OST ideas for it. So yeah, see you in the next video.